Okay, this is the second part of the video segment of buckling of a cylindrical panel with a circular hole. In the first video segment, I made this model. I made the part very simple and then created the plies. And now I'm going to be following the instruction, the problem that I want. Okay, so first thing we're going to do is we'll hide some of the stuff here. So let's see now, where are we here? So let me hide the stacking uh, figure, okay? And then this is my zone. I'm going to hide my zone. Where is the zone? These are the zone that I created. Let's start from the top. Let me hide this. So I have my geometry. There's a couple of more things that are showing here. For example, the boundary I'm gonna hide. The boundary I'm gonna hide, and the sketch I'm gonna hide. Right? These sketches. Yeah, this sketch I'm gonna hide, and yep, and that sketch I'm gonna hide. So something else is showing up here. So let me see. Let me. What is this thing? This is join. Okay, hide the join. I don't want to hide the join, so let's keep it like this for now. Okay, good. Now we're gonna switch to advanced meshing tools and mesh this surface. Okay, so we say okay. Here is the surface measure. You select the surface. This red arrow simply means that the shell elements that are going to be generated here, their normal is in this direction shown, but that's okay. So let's give it a dimension mesh size of 0.5, and we're going to see how it looks like. If necessary, we're going to change it, and then zap it or mesh it. Right here, this looks good. So we're going to exit. So our mesh has been created. Okay, so now we're going to go to generative structure analysis, and to see the mesh better, put the cursor there, right click mesh visualization, and there we are, right there. Okay, let me hide the mesh. Let me hide the mesh or deactivate it. Okay, fine. Okay, so what do we got here? The we're going to import the properties. Import the composite properties. So right there. So import the composite property, and we're going to do it by plies. Okay. Uh, I strongly suggest that you use plies. Okay. So the surface is right there. This is the surface, and plies. You click on the wrench and go and do it by ply. So you go and select your ply group right there, ply group, 16 of them, and you say okay. Again, I advise you not to use the zone, but it's a good idea for you to try it, because I think that at least in the older version, when you were doing the zone, it would go and select that and a sequence that is not what I really wanted. I know that ply works for sure, but zone, I'm not very uh, confident about it. Now, you want it to be symmetrical placed about that surface. Okay, so remember our stacking sequence was like where is that? Like this. So when you select that symmetrical, that means this group, these guys are going to be stacked on top and the bottom of the surface. Okay, so we want to check this symmetry. We say okay. And now we're going to apply our restraint. Okay, so let's see now. Uh, okay, before I do that, I noticed that there is something here that is on the screen, and this will prevent me to apply restraints and loads. So what I'm going to do, this actually happens to be that guy, full price contour. I'm going to hide this, okay? I can put this, right click and hide. Okay, now the edges are accessible to me. Okay, good. So let's see now. Let's go ahead here. And for the, we're doing static case first. So on this edge, ux and uy are 0, okay? Ux and uy are 0. Now notice that the x and y here are not referring to the rosette coordinate system. Oh, wait a minute. I'm sorry. No, this thing says, yeah, global Cartesian system used as the rosette and applying the restraint. Now I did move things around. Remember I rotated these things, okay? And I think the XYZ of that coordinate system that I created, let's check this. Uh, yeah, you see this is the rosette that I used, and that does not agree with this. So what I really want is the global coordinate system. So these things, these that I'm going to be applying are going to be with respect to the global coordinate system, okay? And yep. So let's go ahead. Yes. In a sense, I it says global coordinate system used as the rosette. Unfortunately, when I was doing the problem, I rotated by rosette so that that stuff is not correct anymore. In other words, let me uncheck this. Let me correct this. Okay, use global coordinate system, global Cartesian coordinates, coordinate, coordinates, coordinates, yeah, to apply these things. Okay, so on this edge, ux and uy are 0, and it's global, everything is global here. So here's the user-defined restraint right there. On this edge, ux and uz are, ux and u, what was it? Ux and uy are 0. That's this. Okay, very good. And on this edge, same thing. So as a matter of fact, I can do it again, or I could have selected for this restraint that I created both edges simultaneously. So let me do that. So let me do it again. Same thing. Okay. Ooh, let me check this for a second. Ux and uy. Yeah, uh actually uh actually this is the core. This is should not be global. Okay, so uh, let me take this off. Okay, so simple support based on these things that I wrote down are referring to this coordinate system, which is actually my rosette. Bad mistake here. So let me cancel this. I'm going to go to the restraint that I already created right there. Double click on it. So I don't want global here. I want user. And for user is that coordinate system that I created. Remember I created something and I rotated it. So it's with respect to that. So when I say simple support, and these conditions that referring to that coordinate system, and therefore these are not the global restraints. Okay, so this is what it is. Okay, and while I'm at it, I'm going to do both of these. Okay, so that's good. That's good. But for edges, both of them, let me make sure this is right. So notice that on these two edges, ux and uy are 0. On these two edges, ux and uy are 0, and the x and y are referring to this system, which is our axis system. access one system. It's not the global. I have to eat my words here. Okay, so all right. Now what else do we have? So we said okay. On this edge, UX, UY, and UZ are 0 with respect to that access system. So let's do it here, right there. So all three of them are 0. And it's user again, user, and it's that same coordinate system. Okay, on that's this end. Okay, on this edge, UX and UY are 0, but UZ is allowed to move. So this maybe it was better if I called it NZ here. Okay, because with respect to that coordinate system, this is really NZ. Okay. But anyway, as far as displacement goes, UX and UY are 0. So let's go here. So user defined on this edge, UX and UY are 0, but UZ is allowed to move, and it's the user. And when you say user, you have to go and select coordinate system right there. The bottom line is, I want to emphasize this. I'm sorry I kind of screwed up here, but the bottom line is that these conditions are with respect to that coordinate system, which is the access system that I created. Okay, and that's why I really should have called this thing N or NZ. Okay, with along that direction. Okay, good. Okay, now the first problem that we're going to be doing is the static case where we push in the z direction by that much, z direction meaning the local z direction, axis system, and we want to know what the force is. So in order to be able to push it in the z direction, in CATIA, first you have to make it 0 in the z direction, and then you can change it. So let's see, user defined in the z direction, that edge, 0. Yeah, with respect to user coordinate system, no problem. So we have to select that. Okay. And now that we made it 0, we can go and change it. And that is right there. You see that? Enforce displacement right there. Enforce displacement. You click on it. And let me uncheck that. Okay. So it says what restraint is the last one that I created. Remember, I said 0 in the Z. This is it, right? You select this. And then you say the value that I want is uh, uh, negative, negative 0.0316, negative 0. What was it? 0316, negative 0.0316. And we say OK. Let's save our analysis file, save management, the analysis, save as in that folder that I created. Okay. And hopefully you didn't forget anything. Did I import my properties? I think I did. There's the imported properties, and then we're going to run it. So if everything goes well, this is supposed to compress, and it's going to move in the local z direction, which means in this axial direction by 0.0316. Let's check it. Yep. Okay, so let me change the rendering here first of all. Okay, let's go here. Visualization, average ISO. Okay, change the rendering. Material shade. Okay, so this is the axial displacement deformation. Now, what I want to know, I want to be able to compare it against this. So I need the reaction force at the other end. So this is how we're going to do that. Let me deactivate this plot. Deactivate this. Okay. So we're going to say, okay, I want, put the cursor on sensor, right click, and say reaction sensor. reaction sensor, right? Reaction sensor, and select this restraint at the end where all three of them were fixed from movement. Remember I said on this bottom edge, ux, uy, and uz are 0, okay? And then we say update. What do we have? The force needed in this direction, the force needed in the direction, this was x, right? Local, no, no. Okay, this is with respect to global. I don't want global. Change that to user, and user is that coordinate system that I created, and update. Right there, in the direction Z, because I changed my coordinate system to user, okay? In the direction Z, that's this direction. This is Z direction for user coordinate system. 22412. 22412. Excellent. It works. Okay, so the static case was successful. Now we're going to do a buckling case. The buckling case is I'm going to remove some of these restraints that I put in there. Okay, first of all, for the buckling case, I will go to load and I will delete this user enforced displacement. Delete this. Okay, and then I go down here. Remember, this was I made this thing 0 in the Z direction because I wanted to push in that direction. I'm going to delete that too. So right now we have simple support here, simple support there, completely clamped at this end, not for rotations, of course. And on this edge, simple support, okay? So we're going to apply a force of 1 unit in this direction. Okay, so let's see now. What I mean by force here is force per unit length. So it's this guy, which is enforced line force density. I select this edge and I make it -1. The reason I put it -1 is that later on, whatever multiplier you get, you multiply it by 1 and you're going to get your actual force or force per unit length. Okay, so this is okay. And why don't we do this thing in the user direction? And for coordinate system is that coordinate system that I chose. Okay, so we are applying a 1 unit force Z in this on this edge in the Z direction. Okay, and now we're going to do a buckling insert, buckling case. For reference is that solution that we created. Okay, and we're going to run it. We're going to run it. Done. Buckling right here. Okay, is that I don't like this number that I got, and part of it has to do with the fact that when I applied my force, let me show you here, line force density. What I really wanted to say is -1 lbf per inch. Okay, okay, lbf per inch. I accidentally put the unit of Newton per meter. So now we're gonna go and run this thing. So let me see, everything okay? Yep, we're gonna run this. Okay, so we plotted the translation displacement, double click on it. There we are. So the buckling factor is 1672, okay? And this has a unit of you have to take the, remember I took the 1 pound force per inch, and I have to multiply this 1672 by that 1 pound per inch, and that's right. So how many inches is that? That is let me see, this the length of this arc, is 14.555, okay, multiplied by the nx that I got. So 14 times this number, 14 times this number, 14 times this number. Let me use my calculator and see what it is. 14. I'm really sorry about this. I should have done the calculation. So right here, 14.55 times 1672. I get 24,327 right there. 24, when you multiply that by the buckling factor that you got, this was 1600 something, the calculation gives you 24,327, first mode, 24,3, and it's pretty much this, okay? So all I'm saying is that guy's thesis, it reported the buckling load in pound force. When we do CATIA the way I did it, and I applied 1 pound force per inch, okay, I have to multiply whatever buckling factor that I've got by the length of that arc, which happens to be, in this case, 14.5. I'm matching the results here. My mistake was that when I inputted the force per unit length, I did not realize that it was Newton per meter. So what I wanted to input there was pound force per inch. That's why I went back and repeated that or corrected that box, and the buckling factor came out to be right there. The buckling factor came out to be 1,672, and to get the buckling load and compare it with that fellow's thesis, we have to multiply this times the length of that arc. By the way, these are the other modes. You can see that things become more complicated, and I'm just checking this first one. All right. Good luck and have fun. I'm sorry for this basically screw up that I did. One of them was incorrectly put the unit Newton per meter, 1 Newton per meter as the that initial force that I applied. And the second one is that my coordinate system, you rotated it so that everything had to be with respect to the user-defined coordinate system. I'm sure you're going to be okay.